For number 1, we use Newton's law of universal gravitation. For all the numbers that do not change, such as g, we leave as 1. Since both masses are doubled, I change those to a 2, so 1 times 2 times 2 in the numerator, divided by the distance is also doubled, so 2 squared, so 4 over 4 is 1, therefore the gravitational force remains the same. For question number 2, first thing we need to do is find the acceleration of the mass down this ramp. Now there's really only two forces acting on this mass, force of gravity down and the normal force up. But now if we decompose the force of gravity into its components, we can see that the force parallel to the ramp is mg sine theta. So we use that to calculate our acceleration. So our acceleration is simply the mg sine theta without the mass. Divide the force by the mass. So you use that to find the acceleration. And then once you plug that in, we got to use kinematics to calculate how long it'll take to reach the bottom of the ramp, knowing the total displacement. And we have to do a little bit of trig to find that too. Knowing the height is 5 meters, angle of 30 degrees, we can use trig to find delta x, 5 opposite over the angle or the sine of 30 to find the displacement. So that's a total of 10 meters. And we can see at that point it starts off with an initial velocity of 0. Delta x is 1/2 at squared. And we go ahead and solve for t of 2 seconds. For number 3, we can actually do this a couple ways. We can either use kinematics to solve for v final, or the final velocity, or we can just use energy. Knowing especially that there's no friction or anything like that, we can just use mgh, the potential at the top of the ramp, is equal to the kinetic energy at the bottom of the ramp. That potential energy becomes kinetic at the bottom because energy, as we know, is conserved. So we solve for it and we see that the final velocity is 10 meters per second, using an acceleration of gravity of 10 meters per second squared. For number 4, we know that work is force times distance. Now, one of the key things to remember about using this equation is that the force and distance must always be parallel to each other. So it's asking how much work is done by the normal force. Well, the normal force is perpendicular to your surface. If you're moving down the ramp and the force is perpendicular to the ramp, then we cannot find the work because they're perpendicular. So that means 0 joules of work is done by the normal force. For number 5, we're using the gravitational force, gmm over r squared, and we're setting that to the centripetal force, assuming circular motion in this case. So when we set them equal to each other, we see that the general equation for velocity is square root of gm over r. And then here we're setting up a ratio to find what V2 is. And we have to use V1 in our equation because we don't know what the actual velocity of satellite 1 is. So V2 over V1 is equal to square root of gm over r, square root of gm over r, respectively r2 and r1. And we do a little bit of algebra and we cancel a few things out. And we see that ultimately V2 is equal to V1 times the square root of r1 over r2. For number 6, we're given the frequency and an amplitude. When we're talking about period, the amplitude actually does not matter at all. That just tells us how high or how far from equilibrium this oscillator moves. So all that matters is the frequency. Period is the inverse of the frequency, so 1 over 2.5 hertz gives us 0.2 seconds. For number 7, when dealing with sound, we have to understand that frequency is simply just the pitch. So it doesn't matter what media we go from air to brass or brass to air, the frequency or the pitch does not change. So we look at V is equal to F lambda. Now the speed of sound will change, which will therefore then affect the wavelength. So if we're going from warm air into brass, we're going from 350 meters per second to 3,500 meters per second, that velocity increases by a factor of 10. So therefore, since lambda is on the opposite side of the equation, lambda also goes up by a factor of 10. For number 8, first thing we got to do is draw a free body diagram on both masses. And we're going to go ahead and look at the system as a whole. So Fg1 cancels with Fn. the tensions in the rope cancel out because, again, we're looking at the system. So really your net force is Fg3 minus the force of friction on the other mass. And that's equal to the net force of the system, so mass of the system times the acceleration. We plug in what values we know, and we go ahead and solve for A, and we see that 2.8 mg divided by 4m gives us an answer of 0.7 g. So it's basically 7/10 of gravity. For number 9, the answer is D. Really, this is just a action-reaction problem, Newton's third law. We know that for every action, there's an equal and opposite reaction, so the forces in magnitude are going to be the same. However, the lighter person, less mass, is therefore then going to have to experience a greater acceleration, since force equals mass times acceleration. For number 10, we kind of have to think about force as electrostatic force, KQQ over r squared, but we also can't forget Newton's second law, that F equals mass times acceleration, since really these graphs are comparing the acceleration versus the radius, how far we go away. So because of those relationships, we see that Fe is proportional to the inverse radius squared, and F is proportional to A from Newton's second law. So therefore, we can kind of substitute that and see that acceleration is proportional to the inverse radius squared. So because of that radius squared, that means it is essentially a decaying function. So as the radius gets larger and larger, the acceleration drops with the radius squared. So it's a curved graph, as we see in option A. Number 11 is a static equilibrium problem. We know this mass is hanging from a ceiling by a spring. We know that there's a force of gravity acting down on the mass, and then there's a spring force that's holding it up. Because this mass is in static equilibrium, we set Fg equal to the spring force Fs, so mg equals kx. And we go ahead and plug in what values we know, and we see that x is equal to 0.05 meters, or in other words, 5 centimeters. Number 12 is an algebraic manipulation problem. First of all, we know watts is power, so we think about what power is. Power is simply just how much work is done over time, and work we know is force times distance. Now, since we're given a force and a velocity, makes it a little tough, but we can see in the equation that force times distance over time, that d over t component, distance over time, is a speed, is a velocity, is a rate of change. So we can actually replace that equation and write it as P is equal to force times velocity. So you simply multiply our two values together to get 20,000 watts. Number 13 is a number relationships problem, similar to number 1 from this packet. So an astronaut lands on a planet whose mass and radius are twice that of Earth. If the astronaut weighs 800 newtons on Earth, what will weight be on the planet? So again, what changes, we change to that value. What doesn't change, I keep as a 1. So the mass of the planet is doubled. The radius is twice that of Earth, so r is doubled. So we can see that this force of gravity on the planet is actually half that of Earth. Well, if the person has a weight of 800 newtons on Earth, half of that is 400 newtons. So we go ahead and we can do that in our head. Now, one more quick thing to point out about this. Remember, when we talk about weight, weight is a force, not a mass. Weight and mass are not the same thing, so make sure you remember that. Number 14 is really almost a trial and error type of problem. So we know that there's 4 forces, each 10 newtons. So depending on their direction, in some cases the force might add, in some cases might subtract, depending on the direction of the vectors. But ultimately we see that if we wanted it to accelerate at 10 meters per second squared, that means that the net force would have to be 5 kilograms times 10 meters per second squared, so 50 newtons. Well, if we had all 4 forces acting in the same direction, that will give us a maximum force of 40 newtons, and since 50 newtons is greater than that maximum of 40 newtons, we know that option D is not possible. And you could actually go ahead and draw diagrams to see that, mess around with it a little bit and see that options A, B, and C, if you draw the forces the right way, you can actually get a net force that results in those accelerations. For number 15, we have to remind ourselves, what is a transverse wave? A transverse wave is simply a wave where the medium moves perpendicularly to the direction of the wave. So a good example of that would be like a crowd at a football game, at the football stadium. Now we're talking about harmonics here. We're comparing the ratio of the sixth harmonic to the third harmonic. Now we know harmonics are multiples of the fundamental frequency F1. So the sixth harmonic is 6 times the fundamental frequency. The third harmonic is 3 times the fundamental frequency. So the ratio of those two, 6 to 3, gives us a ratio of 2.